In 1929, Edwin Hubble and his colleagues noticed an important trend in galaxies. Most galaxies are moving away from us, but what Hubble's team saw was that there's a direct connection between how far away a galaxy is and how fast it's moving. The graph at the bottom is from the original paper describing this result. Distance is shown on the horizontal axis and speed on the vertical axis. Notice that as we look at galaxies that are farther away, the speed goes up. There's a lot of scatter in these early results, but a modern Hubble diagram like this one shows that this result holds for much larger distances with much greater accuracy.
Hubble's result caused Albert Einstein to comment that he had made a huge blunder when he first published the general theory of relativity earlier in the century. In that early work, he'd put in a fudge factor into the equations, describing how space and time behave in the universe as a whole, since he couldn't get a stable universe otherwise. But with this new observation, it became obvious that the universe wasn't stable. It was expanding instead, so the fudge factor wasn't needed. So what Hubble saw was not just galaxies moving away from us, but the expansion of space itself. We'll look at the implications of this shortly, but first we need to see just how we measure speeds in astronomy.
Whenever anything moves, the light it emits or reflects is changed by that motion. We call this change a Doppler shift.
For example, if an object moves away from you, the light it emits or reflects has longer wavelengths than when it's staying still. In other words, it looks redder, so we call this a redshift. One way to visualize this is to consider what the waves look like when they're leaving the object. If the object is moving away, then the motion will tend to stretch out the waves, making them longer. Similarly, when something is moving towards you, the light you see from it bunches up into shorter waves. In other words, it looks bluer. We call this a blue shift.
At ordinary speeds, the shift in wavelengths is small, so it's hard to notice this difference, though with precise instruments we can measure it. That's how a police radar gun is able to measure the speed of a car. In astronomy, we typically use spectral lines to calculate Doppler shift. Since we know the wavelengths these are emitted at, we can use them to measure even small shifts caused by motion towards or away from us. The same thing can happen with sound, and since the speed of sound is much less than the speed of light, we can notice changes in pitch for sounds of objects moving towards or away from us, such as that from a race car passing us. Here's the formula used to calculate velocity v from the Doppler shift. C here is the speed of light. Remember that the Greek letter that looks like an upside-down Y is lambda, and it's used to represent the wavelength of light. Lambda naught, the lambda with a small zero subscript, is the wavelength of a spectral line emitted by an object at rest. This is called the rest wavelength. Lambda without the naught is the wavelength of the same spectral line when we measure it with our instruments. This is called the measured wavelength. So by calculating the difference between the rest wavelength and the measured wavelength, we can find the velocity of the object that emitted the light. The units of the velocity will be the same as whatever units we put in for the speed of light. If the velocity is greater than 0, then the object is moving away from us. In other words, the distance is getting larger, and we see a redshift. If the velocity is less than 0, the object is moving towards us, and the light is blue shifted. Note that in astronomy, we often use the term redshift to refer to just the fraction lambda minus lambda naught over lambda naught. The units here all cancel, so the redshift is a number with no units. Let's look at how one of these Doppler shift calculations works. An important spectral line in hydrogen has a wavelength of 656.285 nanometers. If we see a comet that has this line in its spectrum, but the wavelength is at 656.351 nanometers, then we can use this to calculate the speed the comet is moving, as well as telling whether it's moving towards or away from us. So we set up the formula. Then we fill in the values for the wavelengths and for the speed of light. Remember to include the units in the speed of light because that determines the units in our answer. Remember to subtract the wavelengths first, then divide by the rest wavelength to get the redshift, which is 0.0001 in this case. Finally, multiply through by the speed of light to get the comet's velocity, 30 kilometers per second. Also, since the measured wavelength is longer than the rest wavelength, the velocity is positive and the comet is moving away from us. Notice that just a tiny shift in wavelength, much less than 1 nanometer, was enough to give a large velocity. When you multiply by the speed of light, the velocities get big quickly.
Here's your chance to calculate the velocity of a distant galaxy. Once again, we're using the same hydrogen line as in the example, but now the galaxy has shifted this line to a wavelength of over 670 nanometers. First, calculate the redshift, just the wavelength part of the formula. Then multiply this by the speed of light to get the velocity of the galaxy. Remember to show your work and check to make sure that the answer makes sense. Should you get a larger or smaller velocity than we saw in the example? Remember this table? You should be using it to help you keep track of the equations we use in this course. Fill in the Doppler shift section of this table now. Keep it and update every time we use a new equation. You'll find this page useful doing homework and reviewing for exams. Depending on your section, you may be required to submit a copy of the completed version for credit.
We saw a few slides ago that there's a direct connection between how far away a galaxy is and how fast it's moving due to the expansion of the universe. The mathematical formula that describes this is known as Hubble's Law. Hubble's Law connects the velocity of a galaxy, its distance away from us, and a constant known as Hubble's constant. Hubble's constant is really the slope of the Hubble diagram shown on the right. It's also a measure of how fast the universe is expanding. The larger the value, the faster the expansion. The best estimate of the value of Hubble's constant is 22 kilometers per second per megalight year. What this means is that an object that's 1 million light years away will be moving away from us at a speed of 22 kilometers per second. If it's twice as far away, it'll move twice as fast. When we see galaxies appear to be moving away from us, we're really seeing an expansion of the space between the galaxies. A good way to visualize this is to imagine a loaf of bread dough with raisins in it. While the dough rises, the distance between the raisins increases, and the amount the distance grows depends on how far apart the raisins are. If you were on one of those raisins, you'd say that the more distant raisins were moving away from you faster than the close ones. So now replace raisins with galaxies, and you've got a picture of the expansion of the universe.
It's also important to remember that this expansion only becomes noticeable at the distances between groups of galaxies. Within our local group, the expansion rate is small enough that the gravity of the galaxies overwhelms it, so some of the local group galaxies are actually moving towards us rather than away from us. When we look at other groups and clusters, we see the same thing. The galaxies within a cluster aren't expanding apart. Gravity holds them together. But the distance between clusters grows instead.
This also means that when we measure the velocity of a distant galaxy, only some of the effect comes from the expansion of the universe, while some comes from the gravitational pulls of the other galaxies around it. For this reason, the most accurate expansion speeds come from measuring several galaxies in a cluster rather than just one. One of the most common uses for Hubble's law is to calculate the distance of a galaxy. To do this, we have to rewrite the formula to solve for distance. Here's what that looks like. Note that the velocity has to be in kilometers per second, because those are the units in the Hubble constant. For example, consider a galaxy that's moving away from us at 5,000 kilometers per second. To find how far away it is, just plug this value into Hubble's law and divide by the Hubble constant. This gives a distance of 227 million light-years. Remember that the nearest galaxies to the Milky Way are a couple of million light-years away, so this is far outside of our local group and even beyond the Virgo cluster of galaxies.
Now we'd like you to calculate the distance to the galaxy you worked on in the last Your Turn question, the one where you calculated the velocity of a galaxy. See what Hubble's law says about the distance to that galaxy. As usual, make sure you show your work. Remember this table? You should be using it to help you keep track of the equations we use in this course. Fill in the Hubble Law section of this table now. Keep it and update every time we use a new equation. You'll find this page useful doing homework and reviewing for exams. Depending on your section, you may be required to submit a copy of the completed version for credit. Now you should go back through this chapter to fill in the information on the major steps in the cosmic distance ladder.
There is one more key thing we can learn about the universe from measuring the expansion, and that's the age of the universe. The idea behind this is a simple one. Since the universe is expanding, in the past, everything was closer together. If you go back far enough in time, all of space was reduced to a single point, and this time is taken as the start of the universe. The idea that the universe expanded from a single point is known as the Big Bang. We can get an estimate of how long this time has been from the value of the Hubble constant, since that's a measurement of the rate of expansion.
This age is given by 1 divided by the Hubble constant. However, you need to convert the units to get it into a simple time unit. We can do this because the other units in the Hubble constant are both distances, so if they match, then they cancel each other out. Remember that a megalight-year is 1,000,000 light-years. So we do this conversion first. Then we convert light-years to kilometers by multiplying by 10 trillion, or 10 to the 13th kilometers. At this point, the kilometers cancel out, and we're left with units of seconds. This gives us an age of 4.5 times 10 to the 17th seconds. When we convert this into years, it gives roughly 14 billion years. The current best estimate, taking into account changes in the rate of expansion, is 13.8 billion years, very close to the same value.
We're not expecting you to do this calculation, but we wanted you to see where it comes from, and that it really takes just a few steps. Also, compare this time to the age of our own solar system, only 4.6 billion years. This confirms something we've already seen. Our sun is not a first-generation star. It formed out of the gas from many previous generations of stars that died and produced the heavy elements that were needed to make planets like the Earth.